So in the next few lectures, I'm going to explain you the meaning of the poles of a linear time invariant system. So let's say we have a linear time invariant system with a transfer function which has, in the general sense, n poles. And these poles are, as I said in the previous lecture, are equal to the eigenvalues of your A matrix. And if you think about these poles, they are just points in the complex plane, right? The poles are, in the general sense, complex numbers. And these complex numbers can be shown with points on the complex plane. So let me just draw a complex plane here. The horizontal axis shows the real parts of these complex numbers, and the vertical axis shows the imaginary parts. And if you have n poles, that means you have n points on this plane. So some of your poles may be here. Let's say you may have some poles here, and then you may have some poles. But the important thing is, for actual real physical systems, complex poles have to be symmetric with respect to the real axis, right? So you remember that. So if you have poles in these locations, that means the complex conjugates of these poles have to be poles as well. That means you need to have the symmetric of that pole here. Similarly, you will have the symmetric of that pole, and then there will be another one here. So in the end, you will have n points on this complex plane. Now, I'm telling you that where these poles are located give you everything about the dynamics of your system, including its stability property. So by looking at where they are, you can immediately tell whether your system is stable or unstable. And in addition to that, you can tell how that system behaves under certain conditions. For example, if you apply a step input to it, you can immediately see what you expect from that system if you know these poles. Okay, so in the end of this topic, you will be equipped with that information. But to form that information, I'm going to start with a simple example, and then by just we will develop this information based on examples, in other words. Okay, so let's start with the simplest possible case where we have just one pole. Okay, so and then we will see what happens if we have two poles and three poles, and afterwards it will be obvious after a point. Okay, so suppose that you have a first order system. Okay, so I use the spring damper system. Normally this is a second order system if you consider the position of the block. But if you consider the speed of the block y, then the order of the system reduces to 1. So you have a first order equation. And the system can have two types of response, the free response or the forced response. So we will consider both of these responses. Response to initial conditions, this is the free response. Or response to external inputs, this is the forced response. Okay, so from here we take the Laplace transformation to find the transfer function, and the free response of the system happens to be given by this S function. Okay, so as we expected, we obtained an S-domain function, And this S2n function has the first order denominator, which means there's just one pole. This pole is located, according to this function, at minus k over b. So the pole will be on this plane, and it has to be on real axis, right? Because there's just one pole, and if the pole was here, then the symmetric of that pole has to be a pole itself. So we would need to have at least two poles. But since we know that there's just one pole, it has to be on the real axis. So let me just put it here, and this is minus k over b. Okay. Okay, so you can read this part yourselves at home. So let me just jump to the result. Dur ya, hatta şurasını da alayım. Aslında bunu hep gördük ya. Dolayısıyla buraları çok şey yapmıyorum. Fazla detay durmamıza gerek yok üzerinde. So if you have just one pole, then we either need to tell the location of that pole directly, or we can specify the location in terms of time constant. You know, we defined time constant before. And if you write it in this form, s plus something, that something gives you the location of the pole. Or you can write it in this form, tau s plus 1. In this case, this tau becomes the time constant. Okay, it's just the same information. It's the inverse of the other. So the pole is located at minus k over b, and the time constant is equal to b over k. And let's use the time constant because it makes it easier to see the result. If you take the inverse transform of this, you will see that the response is given in time domain with this function. So it doesn't look very clear, so let me just write it again. So y, the response is the initial condition y0 times e to power minus t over tau. And this is for positive values of time. So we see the importance of the pole here already in the form of time constant. If the time constant changes, obviously the response will change. In fact, the response depends on two things only, right? The first, it depends on the initial condition. Then it depends on the time constant. So let me assume that the initial condition is fixed. Let that be 1. And let me choose different values of tau and look at the response. And let me just show it on MATLAB. Okay, so let me define a time vector. Let me choose a time constant. Let this be 1. So I'm going to form this function in MATLAB. This is how I do it. And then let me just plot. This is the response. So we did this before, right? So you can find the value of the output at different time constants, different time instants in terms of time constant. For example, you can see if t is equal to tau, output is something, and t is equal to 2 tau, it's going to be y0 times e to power minus 2. It goes on like that. For example, at t is equal to tau, the output should be at 0.37 times the initial condition. And let's just verify that. Okay, it's not exactly 37, but it's the e to power minus 1. This is that value. So let me change the time constant and see what happens. That means let me move the location of the pole and see what happens. For tau is equal to 1, the pole is at minus 1, and this is the situation we have at hand. We have a pole here at minus 1. In fact, let me use the blue color. And this is the response we get. Okay, so let me choose the pole at, or let me choose time constant equal to 2 seconds. Pole will be at minus 1 over 2. That corresponds to this point. Let me update the value of tau to 2. This is the output, and plot using red. This is the output. Ondan önce bir şey daha tanımlayayım. Hepsi birlikte bakalım. And let's consider the time constant of 3. Okay, so the result actually is consistent with what we expected from our equation. So the output reaches the 37% of the initial condition in one time constant. So for the blue case, time constant was 1 second, so this is what we have. And for the second one, the red one, time constant was 2 seconds, and here it reaches that value at 2 seconds. And for the third one, it is at 3 seconds. Okay? So this is the situation. So we see that the time constant is gives us how fast the system responds to the initial condition. And here we see that if we choose the time, if the pole of the system is close to the real, the imaginary axis, that gives a slow response. If it is far from the origin, then it gives a faster response. In fact, let's try another one, and we will see that it is yet even faster. Or maybe there's no need to try, it's really obvious. Okay, so let's see what happens here. We release the system from the initial condition, and it eventually goes to 0, right? So here the initial condition was fixed, but even if you change the initial condition, the response will not be any different because it is given by the same equation. So if you change the initial condition, then the time dependence is given by this part. So this only changes the initial location, initial condition, but the rest of the response doesn't change. It doesn't depend on the initial condition. So that means no matter where you release the system from, it will always go to the origin. And what origin is, if you think about that, the origin is the only equilibrium point of the system. Linear systems have one equilibrium point, and that is the original state space. So what we actually saw here is the following. If you have, for these three systems, where the pole locations are given here, the system always goes to the equilibrium point. So this means we have a stable system, right? So that's the definition, how we define stability. If you take a system and release it from some point, except its equilibrium point, if it goes by itself to the equilibrium point, that means it's a stable system. So here we saw that for all these three cases at least, the system is stable. Okay, so what if the pole was on the other side? So all these poles are on the left hand side of this complex plane. So what if we had a system where the pole was somewhere here? And let this be plus 1 over 3. That means the time constant should be negative for that case, right? Minus 3, and the pole is at plus 1 over 3. Well, we know actually what we expect from here, right? This time constant is negative, so we have e to power some positive values. And as t grows, the positive value will keep growing. In fact, if our time constant is nerede göstermişiz? Şurada yapardım. So if let's say the time constant is minus 3, at t is equal to minus tau, which means t is equal to 3 seconds, the response will be e to power plus 1, y0 times e to power plus 1, that means 2.7 times y0 approximately. And if the t is equal to 6 seconds, it's not shown here, in that case the output will be e to power 2 plus 2, which will be square of 2.7. It will be a bigger number. So let's plot all these things here. Tau is equal to minus 3. As you see, it starts from the initial condition but keeps growing. Instead of going to the origin, it grows. And if I choose the tau as minus 2, then and then let me try the last one. Tau is equal to minus 1. And let this be black. Okay, so this is what we have. So 2.7 is the level we expect the output to reach after one time constant. And this is really what we expected. If tau is 3, then at t is equal to 3, well, tau is minus 3, the output reaches 2.7. But the other one reaches the same level at different time instants because their time constants are different. Okay? Now let me okay, so this really gives us the trend, and there is one special case which is where the pole is right at the origin. Şunları da tamamlayayım. Okay, so from here we make the following conclusions. I think they must be written somewhere here. Okay, so if a first order system has a negative pole on the left half plane, then the system response converges to 0 and we say the system is stable. If the pole is positive on the right half plane, which means the time constant is negative, then in that case we say that the response diverges to infinity and the system is said to be unstable. And if the pole is at the origin in the middle, then in that case the response is this. It is given by this equation. The exponential becomes 0. E to power 0 is 1. So the output is equal to y0. It's independent of, well, it doesn't change at all. It just stays there. And in that case, the system is said to be marginally stable. Okay, so this is a very important result. At least for first order systems, we can say that if the pole is on the left half of the imaginary axis, which is what we call left half plane, then we know that the system will go back to its equilibrium point if it's released from an non-zero initial condition. And if the pole is on the right half plane, then in that case it will just move away from the equilibrium point, and that's an unstable system. Okay? Any questions? Evet, aynen öyle. So this is only when we have just one pole. And this is only for the free response. We release the system from an initial condition. So if you want to see what happens if we apply an input to this, it is shown next. So I have to be really quick, so I don't want to show the forced response case in detail, but it is already given in the notes. If you have the initial condition is equal to 0, and if you apply a step input, the solution is given here. You again get the response that includes this exponential term. Okay, so the overall function is slightly different, but you still have the time dependence part given by this exponential function. So the same conclusion we obtained from the free response applies here. That means if the time constant is negative, which means the pole is on the right half plane, then the response grows. Or if the time constant is positive, which means the pole is on the left half plane, in that case the response converges to a certain value, and that certain value depends on how big the input applied is. Okay, so at least for first order systems, the picture is really very simple. First of all, we're not allowed to have poles on anywhere besides the real axis, because that requires higher order systems. And on the real axis, the poles on the left half plane are they correspond to stable systems, and the systems with poles on the right half plane are unstable systems. Okay, and not only that, but its exact location also tells us how fast the system responds to inputs or the initial conditions. And if our pole is farther away from the origin, then that means the system will react faster and faster. And if it's close to the origin, then the reaction will be slow. Okay? Because that's exactly related to the time constant. For example, if you have a pole very, very close to the origin, let's say if you have the pole here at 0.01, for which case the time constant will be equal to 100 seconds. That means it will take 100 seconds for the system to reach this level, right? 0.37. It will take 100 seconds for that system. Or if you have pole very far on the left, let's say if you have a pole here at minus 100, in which case tau is going to be equal to 0.01 seconds or 10 milliseconds, and then the response will be really, really fast for that. And this is true for both free response and forced response. So this graph shows the free response, and for the forced response you have the situation shown here. If the input is a step input, then instead of going to 0, the system will go to some non-zero value, and it will be converging to that non-zero value for stable systems, and for unstable systems the system response will be diverging. It will be going to infinity. Okay, so that was the simplest case. Next, let's consider what happens if we have two poles. Okay, so if there are two poles, then we have several possibilities. In the first case, the pole had to be on the real axis. Now it can be anywhere as long as it's symmetric with respect to the real axis. But it can be also on the real axis as well, right? So this is also be a possible pole configuration. You have one pole here and another pole here. Okay, so let's start with that special case. So the system has two poles. They can be both real or a complex conjugate pair. Let's start with the two real pole case. The two real pole case can be studied as superposition of two first-order systems. This is your transfer function. You have two poles, second-order denominator, but you can divide this into two first-order systems. So this has one pole at -1, another pole at -3. And if you apply partial fraction expansion, this is a first-order function, another first-order function. So what you do here is we can use the information we obtained from the previous case here. So you have one pole at -1, another pole at -3. And we know that the response due to these, both of these responses will be convergent. They will be converging to some constant numbers. And how fast they converge depends on the time constant. This will converge more slowly, right? And this will converge faster because it has a pole farther away from the origin. Okay, so let's quickly plot response in MATLAB. I'm going to plot these two responses separately. First, I write these two transfer functions. This is my G1 and this is my G2. Now I define them here. And then I define my input. This is the unit step input. Input is equal to 1 for all time values. And then to find the output, I use the MATLAB LSIM command. Okay, let's see. So they both converge. The first one converges to okay, I'm finding the forced response here, the step responses. So anyway, the response due to the pole at -1 converges with a time constant of 1 second, whereas this one converges to the time constant of 1/3 seconds. And here we can observe that here. So this, as you can see, moves more slowly, whereas this converges faster. And the overall response is the sum of the two. To find the total response, I need to calculate or plot the two. And since this is linear, I can just add the responses together. Let's make this black so it's easier to see. So this is the overall response, the black one. In fact, from here we see that we can also conclude on the stability and the dynamics of the system if it has n real poles. So you can add more poles here. So you can have like another pole here, another pole here, another pole here. Then it will be just the same. We need to have all these responses together. And the general conclusion is the following: if you have two poles on the left half plane, they will both be converging at different rates though. So this will be converging more slowly than this one. If you have an additional pole here, then it will converge as well, but at a different rate. But if you have a pole on the other side, let's say if you have a pole here at plus, I don't know, 1.5, then the response due to that pole will be divergent. And it doesn't matter how many stable poles you have. Even if you have just one divergent pole, that will cause the overall response to diverge. Okay, so you may have like 10 of these convergent responses, but having just one divergent response will may cause the overall response to diverge, because the total response is the sum of all the individual responses. Okay? Ya o niye oldu biliyor musun? Onu aslında çok girmek istemedim de. Madem sordun şey yapayım. Şimdi burada, so what we look at here is the forced response, right? And response to unit step input. So this is the original transfer function. So this is U of S. You multiply this to U of S if you want to find the outputs, and this is 1 over S. So this can be written as follows. First, if you do the partial fraction expansion here, so this is G of S, and you multiply it with the inputs 1 over S. So to find the response, you need to do partial fraction expansion one more time on these two second order functions, right? So this gives you y1 of S, and this gives you y2 of S. And if you do that, if you do the partial fraction expansion on this one and this one, you will find out that y1 goes to a steady value of 3 over 2, and the other one goes to minus 1 over 2. And if you have like 5 real poles, then you just do the same thing 5 times. Then you will have similar things, 3 more of similar things, and then you do the you take the partial fraction expansions and then the inverse Laplace transformations individually, and then you will find out that okay, so let me just write my conclusion here. For a system with n real poles, the response can be found by the responses of superposition of the responses of n first order systems. If all n poles are on the left half plane, all n will be convergent and the system will be stable. If there is a pole on the right half plane, then the response due to that will be divergent, and the system will be unstable. Only one pole on the right half plane is sufficient to make the system unstable. Okay. So as I said, so what we did here is nothing new. So we already did this several times before, taking the partial fraction expansion and then the inverse Laplace transformation. That's why I really didn't spend too much time here. But you can easily convince yourself that if you have an nth order system with n real poles, then this statement is true. So the responses will be given by such functions, and it all depends on where the pole is, because this part gives you the exponential term. And if it has a pole on the right half plane, the exponential term will be growing, and that growing exponential term means that your system is moving away from the equilibrium point, which means that system is unstable. Okay? So let me just stop recording here.